Any questions about anything from last time? Or about anything? Well, today I've sort of been saving this for the right day. I mentioned on the first day of class that one of the great features of analytic functions is that they're conformal. And I told you about the famous Riemann mapping theorem, which says that any simply connected domain that's not the whole complex plane can be mapped by an analytic function one-to-one onto the unit disk. And such an analytic map is conformal, meaning it preserves angles. So it's a mind-blowing thing that if you had a weird-shaped thing with curves all over it, crossing at various angles, that under that mapping, which you think about as like stretching a sheet of rubber, you can stretch it in such a way and plop it on the unit disk so that all those angles are preserved. So I like to think of a map and the angles of roads crossing. Under the map, those roads would go to something different, but they would cross at exactly the same angles. The distances get stretched, but the angles don't. And so the picture for a conformal map is if I have two curves crossing at an angle, at angles alpha there, and notice I'm going to go from gamma 1 to gamma 2. That's also the sense of the angle is going to be preserved. So that's a counterclockwise alpha there, going from T1 to T2 in the counterclockwise direction. Then if I look at where those curves go under F, so let's say gamma 1 goes to F of gamma 1, and gamma 2 goes to F of gamma 2, then those, let's see, I have tangent directions that would, this would be a T1, this would be, I don't know, is that my T2 direction, roughly? I'll call these T1 twiddle and T2 twiddle. Then, amazingly, this angle is going to be exactly the same, and going from number 1 to number 2 is also counterclockwise by the exact same angle. So that's what it means to be conformal. And it's a relatively simple thing to show that analytic functions satisfy this property. Any questions before I get into it? Yeah, it's just a chain rule, basically. And, of course, the Cauchy-Riemann equations are critical in this business, but the Cauchy-Riemann equations come up in this version of the chain rule. So let's suppose I parametrize my two curves. I'll call them gamma j as j goes from 1 to 2. So I'll parametrize them by zj of t. And I'll assume that my zj at 0 is my z0 point. I can always reparametrize so that's the case. And of course we have here j equals 1 to 2. Then I'm thinking of those tangent vectors there as complex numbers. So I represent the tangent vectors. I'm not going to normalize them now. I'll just take zj prime, and that would be at 0. That would be the complex number representing the tangent vector. That's a complex number pointing in the direction of the tangent vector. Okay, so now let's think about where those go. So this is where they start. They're going to go to new curves, f of gamma j, and conveniently those will be parametrized by f of zj of t. And let's see, let's think about the tangent vector. The TJ twiddles, they will be given by d by dt of f of zj of t, plugging in t equals 0. And remember, if you have an analytic function and compose it with something parametrizing a curve, the complex version, and this was the famous chain rule number 2, this is f prime of zj of t. This is the complex derivative, and this other one is the special derivative of a complex function of a real variable, zj prime of t. And of course, I've got to stick in t equals 0. And so that's f prime of zj at 0 times zj prime at 0. And zj at 0 is my z naught. And zj prime at 0 is my tj. So what I get here is that my new direction, tangent vector, is equal to complex number at z naught times tj for j equal 1 and 2. And the aha moment is you realize, aha, I'm multiplying by a complex number, and this complex number I can express as positive radius, and I'm assuming the derivative is non-zero, so it would be a positive r times e to the I out theta. And so we see that just rotates, that stretches by r and rotates by theta. So aha, multiplying by r, multiplying by r e to the I theta stretches the tangent vectors by a factor of r, which is positive, because I'm assuming the derivative is non-vanishing, a factor of r, and rotates in the clockwise direction, counterclockwise direction, rotates. That's assuming theta is positive. If theta is negative, of course, it's the other direction. So rotates by theta in the counterclockwise direction. Of course, if that theta was a negative number, which it could be, then that would be going in the other direction, the clockwise direction. But whatever it is, it certainly preserves that angle, because it means you move them both by the same amount. That angle is preserved. So the angle alpha, the angle and the sense of alpha is preserved. So that's all there is to it. Multiplication by a complex number stretches and rotates. Questions about that? Well, the fun fact is that the reverse of this statement is true. I'm not going to dwell on this. It's just something you ought to be aware of. The reverse is true. And I should say true almost. It's kind of like the Cauchy-Riemann equations, where one direction was always true, but going the other direction, we needed to assume something. And so here's a, so the reverse is true. Let's say I have a conformal map, F, that goes from R2 to R2. Let's say it's given by XY goes to U of XY, V of XY. Then, of course, let's see. Then we have the Jacobian matrix. From Math 261. The Jacobian matrix, I'll call it J, is the gradient of U in the first row and the gradient of V in the second row. And matrix multiplication by by J determines how vectors get treated. So matrix multiplication by J determines how the tangent vectors transform. Transform under F. Okay, and you learned how to do that in Math 261. And so here's the almost part. In order to figure out what we need, we need to assume that the U and the V are C1 smooth. We need to assume U and V are C1 smooth, and the Jacobian matrix has a non-zero determinant. And determinant of the Jacobian matrix is unequal to 0 at Z naught, which corresponds to X naught plus I Y naught. Then it's kind of a high school analytic geometry to show that that matrix represents a rotation exactly when it has a certain form. So it's kind of elementary analytic geometry, which I'm not going to do because this is not the important direction for us. The important direction is if it's analytic, it's conformal. It's just a nice fact to know that if it's conformal, it's analytic. So analytic geometry shows that a linear map is a rotation, preserves angles, if and only if it looks like this. It has the form Jacobian matrix has to look like cosine theta, sine theta, minus sine theta, cosine theta, times a factor. So that R would multiply in every spot. That turns out to be a stretch factor. So if it's a rotation, it also would stretch, like multiplication by a complex number does. And when you look at that matrix for a second, you see the Cauchy-Riemann equations. R cosine theta, that's du dx, is equal to dv dy, which is also r cosine theta. And the other one, that's du dy, is r sine theta, and that's minus what it's supposed to be in the Cauchy-Riemann equations. So we see the Cauchy-Riemann equations here, and that's all there is to it. So that's a fun fact with not a terribly hard demonstration, but just involves a little bit of geometry. Questions about that? Well, you might wonder why I need the derivative to be non-zero. It's a simple example to show you that when something like z squared that has a multiplicity, remember I'm always talking about that kind of map opening like a fan. And those things that open like a fan are going to multiply angles by some number, namely the power. So an example like f of z equals z squared is not conformal at 0 because the derivative is not 0, but so note that f prime of 0, f prime of z is 2z, is 0 at z equals 0. So it's not contradicting my demonstration above. In fact, it doubles angles. And that's easy to check there. It doubles angles at z equals 0. It's conformal everywhere else. It just doubles angles there. And usually a spot like that is going to be in the boundary of a region we're looking at. And so it'll be conformal inside where our mapping has non-vanishing derivative, and on like a corner where it's z squared, well, we don't care if it's not conformal there. So if I did the same routine, let's see, I could do the same routine. Should I do it? Why not? Here's why. Let's say I have z1 of t being equal to some e to the I theta 1 t. I'll parametrize it by that. And my z2 of t, some other angle, e to the I theta 2 of t. At t equals 0, it's at the origin. Then if you look at f of z of t, f of z1 of t, I'll put a zj of t here so I don't have to write it twice. F of zj of t would be e to the I theta j of times t squared. And so that would be e to the I 2, there's the 2, that's the doubling, t squared. And so those two lines get mapped to new lines, and the angle between them, the angle alpha, that would be theta 2 minus theta 1, let's say, gets doubled. Two alpha, that would be 2 theta 2 minus 2 theta 1. And so it opens like a fan. So if I have an angle alpha here, zero, T1, T2, and then z squared would open that like a fan and double it. Let's see, if that's below, I should have made them both above so I could double them. This one's going to go down. This one's going to go up. And the angle's going to get doubled. So it's not conformal. And let's see, you're going to have to consider this same thing in your homework at one point. And so in homework, the last homework, 10, I'll be using z to the alpha. It's going to stretch angles by an amount alpha when alpha is not an integer. So z to the alpha, when they write z to the alpha, they mean the principal branch of z to the alpha. So that would be e to the alpha principal branch of log. That's the principal branch. Anyway, that map expands angles by an amount alpha. Questions about that? Let's see, for the remainder of today, I think I'm going to talk. Yeah.
Which maps do not preserve orientation?
That's a good question. If I had maps which reversed orientation, they would be what we call anti-conformal, and they turn out to be anti-analytic. They're conjugate analytic. So in fact, they would be conjugates of analytic functions. So if you want to reverse angles, you would do conjugate analytic functions. So let's see, I want to talk about a famous map because it gets really used a lot. If you're going to be in science or engineering, you'll probably run into this map. In fact, it's also, we'll see it's important from a theoretical point of view because it has a lot to do with the trig functions. It's called the Joukowsky map. I like to call it J of z is 1/2 times z plus 1 over z. If you think about what it does on circles, you can analyze it pretty easily. On circles, let's see, the Joukowsky map of r e to the I theta would be equal to 1/2 r e to the I theta plus 1 over r e to the I theta. That would be, let's see, that's 1/2 r e to the I theta plus 1 over r times e to the minus I theta. And that's equal to, let's see, I want a real part here. That would be 1/2 times r plus 1 over r cosine theta. Both those, e to the I theta is cosine theta plus I sine theta. And e to the minus that theta, I theta, well, that'd be cosine minus theta, but that's also cosine theta. So there'd be a cosine theta here. That would be the real part. And then we get an imaginary part, which is 1/2 r sine theta would be the first one. And then on the second one, we'd get r of minus theta, which is minus, we get sine of minus theta. And sine of minus theta is minus sine of theta. So this is a minus 1 over r sine theta. And that is the parametric form of an ellipse, which you probably, another Math 261 moment when you were studying conic sections. This is a parametrization of an ellipse. And let's see what do they call that? Suddenly I'm drawing a blank. What's it called? How much skinny the ellipse is? Eccentricity. Yes. When r is close to 1, let's see, that would be, well, I'll have to think about. I'm going to draw a picture which tells you what the eccentricity does. When r is 1, I'd get 1 plus 1, 0. What the heck is that? Well, here's the picture. The unit circle so the units, this is minus 1, plus 1, and 0. Something weird. Oh, yeah. When I stick an r equal 1 there, the second term is 0. The I time is 0. And that first term just goes along the real line. And so that red circle actually gets squished down to a straight line from minus 1 to 1. And the point I gets mapped to 0. So the Tchaikovsky map does that. And if I take a slightly bigger circle, then it's going to be a little squished, an ellipse that looks like this. That would be an ellipse. And if I start drawing much bigger circles, they are ellipses that are kind of circular. Well, this is going to be bad. Darn. I guess I won't go. This is going to be a bigger ellipse, and it's going to be more circular looking. And when r goes out to infinity, they're indistinguishable from circles, because that would be an r plus or minus a 1 over r. And if r was gigantic, that would be r plus or minus something really small. So it would look very more circular as you go out. So this would be more circular looking. Still an ellipse. More circular as r goes to infinity. And these ellipses are the little skinny ones would be more eccentric. And so, in fact, that's a continuous thing, and so the whole the whole outside of the unit disk on the upper half plane gets mapped 1-to-1 onto the whole upper half of the picture on the right. So we see the upper half plane minus the closed unit disk maps 1-to-1 the upper half plane. By that family of circles getting mapped to a family of ellipses. Okay, so the picture is, let's see, I could do, here's a blue line, here's a red circle, here's a green line, and here's plus and minus 1 and 0, and then the Tchaikovsky map would map this picture. It would squish the circular part down to a segment. Let's see, I got a blue, squished, and then green. And this would be minus 1, plus 1. So I probably mentioned earlier in the semester that this famous map is going to be used to, you can study the flow past a circular paddle in a river. So you stick a circular paddle in, and the water flows around it and makes streamlines, and you can figure out what those streamlines are under inviscid flow from this map. And if you spin the paddle, then you can get something called the Joukowsky airfoil, and you can study the lift that's produced by an airfoil. So it's this gets used. Upper half plane, UHP. That doesn't stand for anything. Thanks. The Upper Peninsula. So typically, I have those boundaries in there. It's conformal on the orange part, and the boundaries. Actually, the place where it's weird is plus and minus 1. Then it looks like z squared there. The angles get doubled. So it's conformal on the orange inside part of that thing. Let's see. I guess I should draw the full picture. The full picture would be if I also put in here the bottom half. The bottom half would get squished to the bottom side of it would get squished to that same line. And then this green stuff, I'll make this lime green here. This lime green stuff would get mapped one-to-one onto the lower half plane. And it's just the analytic geometry of ellipses that would determine that. Okay, that's one famous picture of the Joukowsky map. And another famous picture is what happens to the inside of that thing. Let's see, I might as well put it all on the same thing. Let's see, as this green stuff goes out, it would go out here. And as the blue stuff goes out, it would also go out here. And if I put this same blue line in like this time it would go in to 0. And that blue line would get, going into 0, that would get mapped to that blue line going out to infinity on the right. And similarly, the green line going into 0 would get mapped to the green line going out to infinity, one-to-one onto, in fact. And funny thing, you can analyze the map on this picture too, and the top half of the disk gets mapped to the lower half plane, one-to-one and onto. So that's a famous map. Gets used occasionally. And the bottom half gets mapped one-to-one onto the upper half plane. So it's like a 2-to-1 map of the complex plane to itself with some weirdness at plus or minus 1. Those get mapped with multiplicity. And of course 0 gets blown out to infinity, which is kind of interesting to think about. That's the map. Well, one reason this map is important from a theoretical point of view is that we can analyze the complex cosine using it. Function. Let's see. Cosine z, remember, is 1/2 e to the iz plus e to the minus iz. And that's 1/2 e to the iz plus 1 over e to the iz. And when you look at it like that, you realize that is the Joukowsky map of e to the iz. Okay, so here's a famous sequence of maps. If I take a semi-infinite rectangle, I'll take green line going from 0 up. I like that direction. I'll take horizontal here going from 0 to pi. And I'll take a blue line going from pi up. And I'm going to take this shaded orange region here. I times z. Let's say I want to rotate that. If you multiply by iz, I is e to the I pi over 2. So that just rotates that picture by pi over 2 in the counterclockwise direction. So that's going to give me a green along the negative real axis, and then I'll have this going to I pi, and this going like that. So it just flops it over. And now I'm going to take e to the z. And if you think about what e to the z does, let's see, that's e to the x plus iy. That's e to the x times e to the iy. And as x goes from minus infinity to 0, e to the x would go from 0. E to the minus infinity would tend to 0. That's my radius. My angle would go from 0 to pi. So we'd have 0 is less than y is less than pi. And the radius goes from 0 to 1. That's the inside of the upper half disk. So you think about what the e to the z would do to that. It would map to, the red part would get mapped to the unit circle. Let's see, angle pi. Let's see, here's 0 right here. The blue part would get mapped like this. The green part would get mapped like this, go into there, and the red part would start at angle angle 0 and go to angle pi. So I claim the red part would go like this. And of course, this is -1 and +1. And it maps to the inside 1-to-1 onto the unit upper half disk. And now my Joukowsky map I showed you maps this to the 1-to-1 onto the lower half plane. And remember, the circle gets mapped to -1, +1. What happened? The green stuff goes out like that, and the blue stuff goes out like that. And so if you think about it, it's going to be like opening this thing like a dumpster. I open the green one out to the right and open the blue one out to the left and dump it into the lower half plane. That's the feeling. So if you think of that as a sheet of rubber, remember it's conformal. And so these actions of opening that up and dumping it and stretching the rubber out is how the mapping actually works. Let's see if I have to care about the directions here maybe. This one goes that way. This one goes that way. Which way does the red one go? Red one goes like that. And it's 1-to-1 onto. So the complex cosine maps that semi-infinite rectangle 1-to-1 onto the lower half plane. That's kind of mind-blowing. That's the picture. And so, in fact, knowing the complex cosine on that one basic region means we know it for all. We know the cosine z on C now, exactly what it does. Because cosine of minus z is the same as cosine z, and also it's periodic. In fact, the sum of angles formula shows that cosine z plus pi is equal to minus cosine z, and cosine z plus 2 pi, it's 2 pi periodic, so that's cosine z. And so, in fact, here's the picture, famous picture. I won't get fancy anymore. You can get carried away with all the blue and the green and the red. But it's a checkerboard. So let's see, I'll have checkerboard like this. Here's 0, here's pi. I know that this cosine z maps this 1-to-1 onto the lower half plane. By the way, 0 gets hit. So I used to draw 0 red, meaning it didn't get hit by the exponential, but 0 does get hit by the cosine. Okay, that one gets mapped 1-to-1 onto. And cosine minus z is equal to cosine z. So this one is also going to map 1-to-1 onto that spot. And cosine is, 2 pi periodic. And so if I take those and skip one, that's 2 pi periodic. So those get mapped to the same one. And cosine z plus pi is minus cosine of z. So when I take z plus pi, that's this region, that's minus cosine z. So that region gets mapped to minus the orange below. Let's see, so for example, this spot by minus z would get mapped over here. So it's not a reflection, it's a rate, it goes, through 0 as a reflection through the origin. Anyway, all these shaded regions are getting mapped 1-to-1 and onto. And it's just a matter of using those identities to see if you know it on the fundamental semi-infinite rectangle, then you know it, period. And so, in fact, you can read off let's see, the singularity of a function f of z, which is analytic. You think about analytic on a neighborhood of infinity. I call that d epsilon about the point at infinity. That's equal to the z. Let's see. Remember on the Riemann sphere, I called this, it's like a polar cap. D epsilon, a polar cap about the point at infinity, minus the point at infinity. And in the complex plane, that represents the set z such that the modulus of z is bigger than 1 over epsilon. So I should say z in C. The singularity of a function analytic on that punctured polar ice cap is defined to be the type of the singularity of f1 over z at z equals 0. You had to think a little bit about this when you were reading the book, which which I hope you're doing. And if you look at this checkerboard thing, you realize that cosine z has an essential singularity at infinity. So the checkerboard, because it shreds the complex plane. Let's see. We would see that very much like the exponential did. It shreds the complex plane at, well, e of 1 over z, shredded it at 0, which means that the exponential shreds the complex plane at infinity. So what I'm saying is we see that cosine z has an essential singularity at the point at infinity. And in fact, all our favorite question. Oh, yeah, all our favorite functions, sine, cosine, exponential, they all have essential singularities at the point at infinity. And now you might ask, well, what about? Let's see. Can we understand the sine function? Well, if we understand cosine, we understand sine. That's because sine of z is cosine z minus a half, minus pi over 2, rather. You know how to do that? You look at the angles of a right triangle, and this one and this one differ by pi over 2. They add up to pi over 2. Yeah. So that's a trig fact. And that means that if, let's see, if I'm going to take that picture, I would do the same thing, but I'd shift it by pi over 2. And so I would get, make this blue, this green. But now I'm going to go from minus pi over 2 to plus pi over 2. And I'll make these go this way. Make it orange again. Then sine of z is going to map that picture to, and then, let's see, last time it dumped it out and put it in the lower half plane. Sine of z puts it in the upper half plane. And so maybe that makes sine of z kind of better than cosine of z, because this is a prettier picture. It opens, instead of a dump, it just opens like a fan. And it's 1-to-1 and onto. So that's a famous conformal map. You map that semi-infinite rectangle to the upper half plane. And so, for example, we have formulas for solving various things in the upper half plane that we can pull back. So if you're doing some electrostatic problem in a semi-infinite rectangle, you could use this conformal mapping to change it to the upper half plane. We have formulas for the solution, and then pull them back. That's a typical thing that gets done in engineering and science, in 2 dimensions at least. And of course, you get the similar checkerboard when you start extending sine to the rest of the complex plane. Similar checkerboard. Picture on C. When you want to understand sine of z for any z. And interesting, you're always thinking of sine of real angles going from the red part, -1 to 1, but the